In this video, we're going to take a look at the potential energy graph and see how it relates to kinetic energies and how we can solve problems involving this graph. So for this example, we're going to take a potential energy graph that looks like U of x is equal to 4 over 2 plus x. So we've seen, this is a little unfamiliar, we've seen equations that look like this. U equals 1 half kx squared for a spring, so it's a spring system. So this is something a little bit different. Not sure what the system is, maybe a ball and a wrap or a different type of spring, but we do know the potential energy equation for it. So let's stick with this one right here, and let's take a look at what the graph looks like. So let's see, when x is 0, let's graph it. When x is 0, we get the value of 2. When x is 1, we get 4/3. So let's see, x is 1 a little more than, right around here I think it is. When x is 2, we get the value of 1. And when that value is 3, we get 4/5, a little bit less than 1. Okay, so we get something that looks like it's a 1 over x type function that decreases here like this. All right, so the question is this: for whatever the system is, we want to find if the velocity at 0 equals 0. So if it starts from rest, so at this point right here, if the velocity is 0, 0, we want to find the velocity when x is equal to 2. So when this object does get to this point, value of 2, how fast is it going? So, solution. Okay, so this is a conservation of energy type problem. So what we're going to say is, we know some information here at point 2, so I'm going to draw 2 buckets here. I'm going to draw a kinetic energy bucket and a potential energy bucket. Now normally I would do a gravitational and elastic, but I'm not sure what types of potential it is. I just know the total is a value of 2 at this point. So I'm not going to differentiate between gravitational and elastic. It's just the total is 2 there. And over here, and we have no kinetic because it's a start from rest. And at this point here, I'm going to draw 2 more buckets. And again, a kinetic and potential. So potential, I know how much it is. It's a value of 1. This is 1. This is 2. So this is, if we have conservation of energy here, this is going to be a value of 1. So formally, if you want to take a look at this, call this point A and call this point B. I can say the energy at point A is equal to the energy at point B. And again, I'm going to worry about the kinetic and the potential. And this is all the potential. Well, however, the potential is split up between gravitational or spring or any other type of potential. That's the potential here. So we have kinetic, nothing to start with, it's at rest. Potential is a value of 2. Kinetic is, this we know is 1, and so this is value got to be 1. So quantitatively we have 2 is equal to that unknown kinetic, which we, in this simple case, we know it's 1, plus 1. So the kinetic energy when x is equal to 2 is equal to 1 joule. So anytime you have so the numbers here are pretty simple, but anytime you have a potential energy graph and you need to analyze the different types of energies at 2 points, just draw buckets right on the graph, your kinetic and your potential, and then you can analyze the problem just like a typical conservation of energy type problem.